Hello everyone, welcome to my channel Simplified Organic. Learn organic in a simple way. So today's lecture is lecture number 3 of Geometrical Isomerism. Already I have uploaded 2 lectures of Geometrical Isomerism. In that we have learned how to identify whether a compound can show Geometrical Isomerism, and if it shows, how do you nomenclature, how do you give the IUPAC nomenclature of that geometrical isomer. So those two videos link I will be adding in the description box. Please go through that. And today it's geometrical isomerism lecture number 3, in which I'm going to discuss about the calculation of number of geometrical isomers. Calculation of number of geometrical isomers. So if a compound is given which can show geometrical isomerism, and if you want to find out how many isomers are possible, geometrical isomers, then we have to use some formulas to calculate them. What are they? So the first condition is, if the ends are different, like for example, there is a compound, an alkene, conjugated alkene, IUPAC name 1, 2, 3, 4, 5, 6, 7, hepta 2, 4 diene, heptadiene. So if the question is given how many isomers are possible for hepta 2, 4 diene, so you need to check whether the ends are same or different first. So these ends, this side there is a methyl group, and this side there is a ethyl group. Excluding this conjugated system, we have to check. Excluding this is a conjugated system. This is the conjugated system. So on either side of this conjugated system, if the ends are different, then the formula is 2 power n, where n is the number of pi bonds, I can say, or number of stereo centers. So in this case, the number of pi bonds are 2. So 2 power 2, that is equal to 4. So total 4 isomers are possible. Now what are these 4 isomers? If I want to write them, how can I write? See, first of all, I can represent that molecule in this way. 1, 2, 3, 4, 5, 6, 7. So what are the positions of the double bond? The positions of double bond are 2 and 4, right? So at second position, it is looking like a trans. See, at second position, it's like a trans. Or I can also say it's like a E form, right? So I'll represent it as 2E. Okay. And at the fourth position also, it looks like a trans. See, the fourth position also it's look like a trans. So I'll call it as 4E. So the designation, the IUPAC representation of this molecule is 2E4E. What is this E and Z forms? I have already discussed in my previous lecture. Please go through that. And the second way I can represent the molecule is in this way, wherein 1, 2, 3, 4, 5, 6, 7. So in the second position, it is like a trans, so 2E. In the fourth position, it is like a cis 4Z. So this is called as 2E4Z form. And I can also represent this molecule in this way. One, two, three, 4, 5, 6, 7. So it's like a 2Z 4E. See, it's like a cis here. At the second position, it is like a cis. And at the fourth position, it is like a trans. Therefore, it's called as 2E4Z. And lastly, I can represent it as look at the positions of the double bond and the orientation across this double bond. That is 1, 2, 3, 4, 5, 6, 7. So here it's like a cis, and here also it's like a cis. So overall it is 2Z and 4Z forms. So total 4 isomers are possible: 2E4E, 2E4Z, 2Z4E, and 2Z4Z. What are these Z and E and Z forms? This I have already discussed in my previous lecture. Please go through that to understand these. Now coming to the next condition, that is, if ends are same, if ends are same. So in these two conditions are possible, where n is even, we have a formula, number of geometrical isomers equal to 2 power n minus 1 plus 2 power n by 2 minus 1, where n is the number of pi bonds or number of stereo centers. We'll go for an example like CH3, CH double bond CH, double bond CH, and then CH. Now excluding this conjugated system, this side you have methyl, on the other side also you have methyl. So ends are same. So definitely you will use this formula, that is 2 power n minus 1 plus 2 power n by 2 minus 1. So n is 2 here. There are 2 pi bonds. So n equal to 2. So 2 power 2 minus 1 plus 2 power 2 by 2 minus 1. So the answer is 3. So total geometrical isomers possible are 3. So let us draw these 3 geometrical isomers, like I have done for the previous example. That is, I can represent it as 2E, right? And 4Z, 2E, 4E, 2E, 4E. I can also represent it as 2E, 4Z. And lastly, I can represent it as 2Z, 4Z. Now students will get confused with this here. They think that we can also represent it in this way. So they feel like that it's 2Z4E. Actually, which is wrong here. Here I can number these two, this compound from both the way. If I number from this, it's 1, 2, 3, 4, 5, 6, right? And if I number it from this direction, 1, 2, 3, 4, 5, 6. So it's like 2E4Z, same only, right? So students will get confused here. Because ends are same, I can number them in any direction. As the ends are same, can number it from any direction. and number it from both the direction. Okay, so these two are same. So we have to count it as 1. So total 3 isomers are possible when ends are same. As I told you, when ends are same, there are two formulas, two conditions. When n is even number. When n is even number. So what if n is odd number? So condition number 2. If n is odd number. Like for example, the simple and smallest example is the butene. If I take the example of butene, what is the n value? N value is 1. CH3, CH double bond, CH, CH3, right? Here the ends are same. Ends are same. And the n value is 1, n equal to 1. So now what is the formula? The formula here is number of geometrical isomers is 2 power n minus 1 plus 2 power n minus 1 by 2, where n is the number of. So if you apply it here, you will get 2 power 1 minus 1 plus 2 power 1 minus 1 by 2, right? So what is your answer? It's 2. 2 isomers are possible. What are these 2 isomers? You are very much familiar. One is cis and the other one is trans. Cis and trans form. I can also apply the same formula to a compound like this. If I take this conjugated system 3 times, this whole 3 means I'm talking about 3 pi bonds in conjugated. 3 pi bonds are in conjugation. 3 pi bonds are in conjugation. So anyway, ends are same. So apply the formula n equal to 3, 2 power 3 minus 1 plus 2 power 3 minus 1 by 2. So total 6 isomers are possible. I'll not draw those structures, but I can represent it in E and Z forms. So the first one is, it can be E form. The second one, it can be Z form. Third one, it can be EZ, which is also equivalent to ZEE. And the other one is ZZE, which is also equal to EZZ form. Fifth one, EZE, the fifth possibility. And the sixth one is ZEZ. So total 6 isomers are possible. So in this way, you can easily calculate the number of geometrical isomers. So once again, a recap. The first formula is 2 power n when ends are different. Very simple. When ends are different, the formula is 2 power n. When ends are same and n is even, n minus 1 plus 2 power n by 2 minus 1, where ends are same and n is even number. The third, 2 power n minus 1 plus 2 power n minus 1 by 2, when ends are same and n is odd number. So in this way, you can calculate the number of geometrical isomers for a given compound by using these formulas. So that's all for today's. Remaining we'll see in the next lecture. Do subscribe and like my channel and share as much as possible. Thank you very much. Bye bye. Take care.